Hey Chemistry! So today we are going to finish up chapter 13 and learn about phase changes. After this you will be getting your VA. Your VA is going to be due on Wednesday. Also next Wednesday we are going to have a review session at 9:30 and then you are going to have your test on chapter 13, alright? So, hopefully you'll be able to spend, and your VA is going to be your only assignment after you finish with this JunoPod. So, essentially tomorrow, Monday, Tuesday, your only assignment is just to work on your VA, so that should be plenty of time. I'm here if you need any questions, but we also will have that live meeting on Wednesday morning, and then you'll have your test next Wednesday, alright? Okay, so let's do this. Phase changes. Suppose you take a glass of ice water outside on a hot day. We all know what happens. The ice has melted and it looks like there's less water in your glass. Can you use the kinetic molecular theory to understand what happened to your drink? Most substances can exist in 3 states depending on the temperature and pressure. A few substances, such as water, can exist in all 3 states under ordinary conditions. States of a substance are referred to as phases when they exist as physically distinct parts of a mixture. So ice water is a heterogeneous mixture with 2 phases, solid ice and liquid water. When energy is added or removed, one phase can change into another. So because you're familiar with the phases of water, we can use water as the primary example in the discussion of phase changes. So first we're going to talk about phases that require energy. Number 1, melting. You should be pretty familiar with what melting is. It's what ice does in a glass of water, right? The energy absorbed by the ice is not used to raise the temperature of the ice. Instead, it disrupts the hydrogen bonds holding the ice molecules together. When the molecules on the surface of the ice absorb enough energy to break the hydrogen bonds, they move apart and they enter the liquid phase. So what's actually happening is the energy is disrupting the bonds. The energy is disrupting the bonds between the ice that's holding it together as a solid, and it actually breaks the bonds enough to make it a liquid. The amount of energy required to melt 1 mole of a solid depends on the strength of the forces keeping the particles together, right? So there's a super helpful diagram underneath there on page 404 that talks about how to go from one thing to another. Okay, so melting is specifically a solid to liquid. That's what happens. You don't melt into a gas. All right. The temperature at which the liquid phase and solid phase can coexist is called your melting point. The melting point of a crystalline solid is where the forces holding the crystal lattice together are broken, so it becomes a liquid. Number 2, that requires energy, vaporization. In vaporization, you go from a liquid to a gas. And you do need to know all of these, all right? You're going to need to know them. When ice melts, the temperature of the ice-water mixture remains constant. Once all of the ice is melted, additional energy creates kinetic energy in the liquid molecules, and what happens when they increase their temperature and the kinetic energy goes bigger? They escape from the liquid and they enter the gas phase, and that's vaporization. When vaporization occurs only at the surface, that's called evaporation. Even at cold temperatures, some water molecules have enough energy to evaporate. As the temperature rises, more and more molecules achieve the minimum energy to escape. Evaporation requires energy, is the means by which your body controls temperature. When you sit outside and you sweat, water and sweat can absorb the heat energy from your skin, and then when it evaporates, you are cooler. Not only is the heat transferred from you to the cooler water, but the water molecule, water molecules in sweat can absorb heat energy from your skin and evaporate. Excess heat is carried from all parts of your body to your skin by your blood. Evaporation of water also explains why a swim in the cool ocean is so refreshing. Not only is heat transferring from you to the water, but the water molecules left on your skin start to evaporate when you leave the water. The salts that remain often leave like a white residue, so when you swim in the ocean, you've got a little bit of salt on you. That's because the water evaporates, but the salt doesn't. Okay, the picture on page 406 compares evaporation in an open container with evaporation in a closed container. So basically, water vapor can collect above the liquid and exert pressure on the surface of the liquid, and that can be called vapor pressure. So the temperature at which the vapor pressure of a liquid equals the external or atmospheric pressure is going to be your boiling point. So that's when water starts to boil at 100 degrees Celsius. At the boiling point, molecules throughout a liquid have enough energy to vaporize. Bubbles of vapor are going to collect under the surface, and those are the bubbles that you see. And then, so that's vaporization. It includes vapor pressure, boiling point, evaporation, things like that. Now we're going to talk about sublimation. Okay, sublimation also requires energy. And sublimation is when you go from a solid to a gas. All right? So, solid to gas. Solid iodine and solid carbon dioxide, dry ice, that sublimes at room temperature. The special effect is, so basically when dry ice sublimes and cools water vapor in the air, creates a really cool effect. Dry ice keeps objects that could be damaged by melting water cold during shipping. Mothballs, air fresheners, things like that. If ice cubes are left in the freezer for a long time, they shrink because the ice sublimes. At extremely low pressure, ice is going to sublime. The property of ice, that's freeze drying, okay? So that's kind of how that works. So sublimation is going directly from a solid to a gas without moving through the liquid phase, okay? So those are your three phase changes that require energy. Now let's talk about phase changes that instead of requiring energy, actually release energy. And there are three here as well. Number one, condensation. So condensation is when you are going from a gas to a liquid. And you've probably seen this happen. When a water molecule loses energy, its velocity is reduced. That vapor molecule is much more likely to interact with other vapor molecules, form a hydrogen bond, and begin to create liquid water. And that's the process called condensation. It's basically the reverse of vaporization. There are different causes for condensation, but they all involve a transfer of energy. Sometimes if you have something condensing in a glass, the heat from the water vapor is going to be transferred to the actual glass, and so that is where your energy goes, okay? That's where like dew comes from, fog, those are all made through condensation, clouds, things like that. Another phase change that releases energy is deposition. Deposition is going from gas to solid. So it's actually the reverse of sublimation, okay? So that's how that's going to work. Deposition is you go gas directly to solid. You don't become a liquid at all. So for example, water high up in the atmosphere can change directly into solid ice, or water vapor high up in the atmosphere can change directly to solid ice crystals. That would be an example. And then we got one more. What happens when we go from liquid to a solid? This is a term that you've definitely heard before. It's called freezing. So, when something freezes, the freezing point is the temperature at which the liquid is going to be converted into a crystalline solid. The molecules are less likely to flow past one another, and you're going to start forming these stronger bonds and making those unit cells. Okay? So, phase diagrams. There are two variables that combine to control the phase of a substance: temperature and pressure. Okay? So, phase controls and diagrams. So you usually have, if you're going to have a diagram, it's going to be a graph. It's going to be a graph of pressure versus temperature. Okay, so a phase diagram is a graph of pressure versus temperature that shows where a substance is going to be in each phase. So you're going to want to look at page 409 in your book. They color code it for you. The blue At that combination of temperature and pressure, that substance, water and carbon dioxide, is going to be a vapor. In the green, anywhere in the green, that's when it's going to be a solid, and in the yellow is when it's going to be a liquid. Note there's 3 separate regions, but at one point everything intersects. That's point A in the phase diagram for water, and that's called your triple point. That represents the temperature at which all 3 phases of the substance can coexist. All 6 phase changes can occur at the triple point. If you have that exact combination of pressure and temperature, you can have all 6 of these phase changes happening. It's kind of crazy. The phase diagram for each substance is different because each substance has a different freezing point, boiling point, everything like that. It's all going to be different. And so the phase for everything is going to be different. So there's a couple of questions in your GenoPod that ask you to look at that diagram on page 409 and analyze what that data is. Okay? So that's the end. That's the end of the chapter, just talking about phase changes. So hopefully that wasn't too bad for you. And yeah, good luck. You'll get your VA some point later today, and we'll go from there. All right? Good stuff, you guys. I will talk to you soon.